There's a lot of people that joined us here today to roll out the results of the last 4 years worker health study. We have 4 members from the science committee, the panel that's been overseeing the study and that selected the contractors and selected the scope of work for the research team. We have Dr. John Boice, who's going to be presenting. He's the principal investigator from the International Epidemiological Institute. We have Dr. Craig Conlon, our medical director up here that most of you probably know. We have Barbara Ludwig, our industrial hygienist, who helped put the chemical side of the study together. Phil Rutherford, the manager of radiation safety. We have next to Phil, Byron Wood, our general manager and vice president here. And so Byron's joined us. This is the first rollout of the full employees meetings. We had one short one yesterday with about 25 people who participated early on in the interviews, mostly retirees. But this is a milestone. This is 4 years and $3.5 million later after we got together the first time after the UCLA study, and we said, you know, the UCLA study raised a lot of questions. And so we wanted to go forward and try to answer some of those questions. And so that's what's brought us to this point in time today. It's important to understand that the whole study was sponsored by the Boeing Company and the United Auto Workers. Frank Meyer, who's the director of health and safety back in Detroit, was unable to be with us today because of a last-minute change in his stuff. But we are fortunate. We got George Bounds, the president of 1519, sitting in the back row back there. We have Linda Hayes in front of him, the health and safety representative, and the UAW and us got together and we wanted to have no fingerprints on the study. We didn't want Boeing to interfere with the study, so we appointed 3 science panel members, and the UAW appointed 3 science panel members, and those guys took over, and we're going to have them explain to you what they did in just a second. But it's been a real experience for me to listen to the brain power involved with the study and the direction that the study has taken. And I guess with that, I'll introduce Dr. John Peters. He's from the University of Southern California. He's a professor and director of the Division of Occupational and Environmental Health in the Department of Preventative Medicine. Dr. Peters coordinated the science committee, who's also sitting in the front row with him here, for the oversight of the study and the research team itself. And so he's going to talk a little about the science committee and how this process was worked through, how they came up with the team and the study and the scope of work, et cetera. So with that, I don't think you need that.
Okay. Thank you, Steve. I want to introduce the 3 members of the science committee that are here today. Carl Kelsey, please stand up or wave. Scott Davis and Jack Simiotiki. The other 2 members that couldn't come are, like the 4 of us, we're all full-time university people. Professors do teaching and research, and we spent a few days a year for the last 4 years trying to help in this process. As Steve mentioned, one of the things that we did is sort of set up the scope of the study, tried to identify the best group or set of researchers to do it, and that's John Boice and his group that you'll hear from in a moment. And then we've monitored the progress of the study. I think it's fair to say that none of the 6 of us know whether the union or the company nominated us. And it doesn't really matter because, you know, independent science is what we're all about and what we're trying to do. I think there are just 2 or 3 points that I'd like to make. The usual process was for us to sort of review things annually, see what the progress was, ask a lot of questions, and we would frequently hear from John Boice what was going on, and then we'd have a private session with the science committee to decide what questions or issues that we had. We'd present them back to John, and I'd say that process worked very well from our point of view. Everybody listened. There were responses to our questions and issues, and things moved along nicely. All the way to the end, and not to say that the end didn't end well either, but it did. So I think we're all happy and have agreement on the way the findings have been presented. There are a couple of things that I should mention. We took it upon ourselves to write a separate independent review of the study, which is maybe slightly different from the IEI version, but not much. There's general consensus. And this document is on the table if you'd like to read it. You can compare what IEI said with what the science people said. And I think it'll be very difficult for you to identify any real differences. So I think that's important. And then I think the last thing that I wanted to, well, two things that I wanted to say. One is that we got lots of support from both the union and the company through this process. It was, from our point of view, we had an independent role and nobody put any constraints on what we did or our activities. And I also would like to commend IEI for doing a thorough, excellent job, and you'll hear about that in a moment. And if not, thank you.
I'm an epidemiologist, and 4 years of my life I have spent studying the Rocketdyne workforce. And it's been a rather wonderful and enjoyable experience, particularly meeting in the many sessions we had with the workers, both retired and active. I'm now going to condense 4 years of my life into 20 minutes. And so if there are some unanswered questions, I'll be available afterwards and try to answer any of them that might come up during the presentation. When we did the study, though, it involved quite a number of research scientists, over 20, about 25. To do the radiation exposure assessment, we worked with the Oak Ridge National Laboratory in Tennessee. We also worked with the Oak Ridge Associated Universities in Tennessee. To do the industrial hygiene, we worked with IHI, which is a large industrial hygiene group out of Salt Lake City in Utah. We had consultants from USC, the University of Southern California, from Vanderbilt University, and also from Lovelace Labs out of Albuquerque. So we had assembled a large team on this collaborative effort. Working with the science committee is what I'm going to be presenting to you in the next 20 minutes. Okay, who was in the study? We worked with the Rocketdyne staff and assembled just a wide range of personnel records, Cardex cards, computerized files to identify some over 50,000 workers from 1948 to the current time, or till 1999. And we studied 47,000 workers to be eligible. They had worked more than 6 months, either at Santa Susana or with radiation or Canoga Park and the surrounding areas. Of those, 5,800 had been monitored for radiation and were included in the study. 8,300 had worked at Santa Susana. And many of you, I'm sure, are included in our study if you were actively employed as of 1999. And for a comparison group in some of our analyses, we had the workers from Canoga Park, DeSoto, and the other small surrounding areas at Rocketdyne. So we had 47,000 workers from this long period of time. We had to trace them. We had to locate them. And so one of the successes of our study is using national and company resources. We located over 99% of all workers using Social Security, Healthcare Financing Administration, Rocketdyne records, California state information. So it was very successful with regard to the completeness of our follow-up. Now I'm going to talk a little bit about exposure assessment. First I'll talk about how we approached determining the amount of radiation the workers received, and then how did we approach determining the amount of chemical exposures workers received, mainly from working on test stands. In terms of radiation, there was two types that we were concerned about. One is the so-called external radiation, or penetrating radiation. This comes from outside sources, radionuclides or reactor emissions, something outside the body. Internal exposures would be if you're working with these radioactive materials, and from inhalation or ingestion, you might have taken them into your body and they would lodge in the lung or perhaps other organs, giving radioactive dose. So we had an intense exposure assessment for internal radiation with Oak Ridge and spent several years evaluating the biological samples. You know, people that had the potential for exposure to internal radiation, they had urine samples taken and fecal samples, whole body counts. So we put all that information together to try to estimate what the radiation dose was to various organs. How about the external? You know, back in the days in the 1950s and 1960s where nuclear energy and nuclear technologies were being developed, there was a lot of workers that worked at a lot of different places. So people came to Atomics International with work experience elsewhere, such as at Hanford. And then they left Rocketdyne, and they went to other places, such as Idaho Falls or a nuclear utility. And in those other places, they received additional radiation exposure. So one of the strengths of our study, we went and sought the radiation doses people received after they had left Rocketdyne or when they came here. And so it turned out of that workforce, you know, we said 5,800 people had been monitored for radiation. 1,700 had radiation doses elsewhere. And of those, 25% of them had more dose elsewhere than they had at Rocketdyne. And we tried to take all that information into account in terms of assessing the exposures. What were the numbers once again? Was 5,800 monitored for radiation. Practically everyone was monitored for external radiation. But there were about 2,000 workers, a little over 2,000, who had been monitored for the possibility that they had ingested or inhaled radioactive materials. There was just a very small number, just a little over 50, who had only been monitored for internal radiation. So that's how we looked at radiation. How did we look at chemicals? Well, first we just had this general category of anyone who worked at Santa Susana, and that was sort of called the chemical cohort. Just by being here on the hill, there was a possibility through the testing of the rocket engines over all these years that there was some low-level or high-level exposure to various chemicals. So we looked very carefully at everyone who worked at Santa Susana. And then through the interviews and the discussions with workers, it was determined that the group that was most likely to be the most heavily exposed to chemicals were the test stand mechanics, the guys who had the hands-on experience, who were hooking up the hoses, who were working with the fuels, working with the oxidizer, the exhaust gases, all of that. So they were highlighted, the test stand mechanics as a group, and there's about 1,600 of them, that we were going to look at very, very carefully and try to assess the amount of chemical exposure they might have received. Well, we broke it down. There's two types of chemicals that we focused on. The hydrazines, very toxic chemical that was used mainly in the small engines, but it was used throughout the years. And then trichloroethylene, TCE, a solvent. Now, the solvent, was used to clean the large engines from the hydrocarbons, and also was used as a utility solvent to clean small parts. And so we were able to identify individuals who had the potential for exposures to these chemicals. How did we do it? Well, we have your work histories, job histories, Cardex cards, or personnel lists. But there was a very fortuitous find. It was found a stack of phone books, personnel listings, going back to the early 1950s, which had the test stands that individuals worked on. And so we could then link up the names of a test stand mechanic to an actual test stand, whether it was Alpha or CTL4 or Bravo. And because of that, and knowing the calendar year, and knowing what chemicals were used for that calendar year at that test stand, we then were able to assign an individual saying, these individuals, about 25% of them had hydrazine potential exposure. TCE, was about 75-80% people in the study had potential exposures to these solvents. So that was another additional enhancement of our study, that we were able to use the phone books identifying individual workers to test stands with the potential for exposure. Again, I just mentioned we had really informative discussions with retirees and current workers. We brought them back to the Radisson Hotel there and had lunches and informal sessions where we did show slides like this and asked for thoughts, ideas, memories, experiences, telling us how they worked with chemicals, how they worked with radiation, giving us leads, and through some of these sessions we identified some of the phone books. And so it was extremely useful, extremely helpful, and most enjoyable. How many people were in the so-called chemical cohorts? Well, overall at Santa Susana there was 8,300 workers from 1948 through 1999. Of those, 1,651 could be identified as test stand mechanics. Sometime during their career they had worked on one of the test stands. Those with the potential exposure to TCE, there was 1,100. Many workers had the potential for exposure to these chemicals. And you'll note that I'm using the term potential. These chemical exposures, are different from radiation. Radiation, we had a badge or we had a urine sample where there was radioactivity measured, so we could kind of make a good estimate of the amount of radiation a worker received. From the chemicals, there weren't any chemical badges, and in the early years, there was very little sampling. So all we could estimate was they had the potential for exposure because they worked with chemicals that were present at the test stands. With hydrazines, there was 317 workers who had worked with hydrazines. We could definitely assign potential exposure to them. There was another group, 200, and you'll see this group come up again. And that was a group we weren't able to make a determination. On some of the large test stands, there were limited areas where hydrazines were used, but they weren't used in general. So there's only a few workers at some of the large test stands that actually had been working with hydrazine. And so we estimated that in these groups it might have been just 10%, or about 15 to 20 of these 200 workers actually had worked with hydrazine. But the phone books weren't that accurate and we couldn't determine who was who, so we put them as an intermediate category. So that was the exposure assessment. Again, here's the three groups that we evaluated during the past 4 years. We evaluated them by getting their personal information so we could trace them, getting their information to make exposure assessments, and then determining who died and who did not die so we could do a mortality analysis. There's 5,800 in the radiation group, 8,300 workers at Santa Susana, and the Canoga Park and the other groups of workers in the surrounding areas, almost 33,000. Now I'm going to show you a series of slides, and they'll all have the same patterns. These slides with these horizontal bars are showing the observed number of deaths with the number that would be expected had the workers experienced the death rates that were present in the general population of California. So the top bar is in the light blue. That indicates the observed numbers of deaths. And so for all the Rocketdyne workers that we studied, 11,000 had died. Of the 47,000, 11,000 were found to have died, and we obtained the cause of death for them. Based on rates present in the general population of California, about 12,000, a little over 12,000 deaths would have been expected. So this indicates that Rocketdyne workers in general have a much better mortality experience, are healthier, if you will, than the general population of California. This was true not only for all causes of death, it was true for all cancers and for specific causes of death, lung cancers, liver cancers, leukemias. When doing studies like this is not necessarily surprising. It can be related to what's called the healthy worker effect. Just by the fact that you guys and women are here and you're able to work, that makes you a little bit healthier than the general population. And as longer you're able to continue your work, that shows a selection, if you will, on health. And so when you do worker studies like this and compare with the general populations, you usually find a better experience from the workers. Okay? Once you retire, however, and as you get farther and farther away from that time of employment, this healthy worker effect, if you will, kind of diminishes, and that's particularly seen for causes of death due to cancer. So after employment, this healthiness that's related to employment disappears a little bit. Okay. So this was for all Rocketdyne workers together. I'm going to be showing you similar slides. What about the radiation workers? What are the guys about the guys who worked on the Hill? What about people who work with hydrazine? So it'll be the same sort of pattern. And then I'll be showing what's called dose response curves, which will be the most important factor that we used in determining whether or not there were health hazards from the exposures. Here's the radiation workers. Again, very similar to all workers at Rocketdyne, they had a lower risk of death than the general population of California. And this was true for all causes of death. These are now 5,800 workers, about 1,400 had died. They had a lower mortality than the general population of California, lower risk of dying of cancer, and the lower risk of lung cancer and even leukemia. There was 18 versus 16. A slight excess of leukemia, 1 or 2 cases, was not statistically meaningful and could be attributed to chance. The Rocketdyne Atomics International radiation population received very low doses of radiation. That's an extremely important point. In comparison to other radiation studies, other occupational groups, the exposures received at Rocketdyne, and even when we incorporated the exposures they received elsewhere, it's very low. And so you can see in this distribution in the first column of the 3,800, these are all in the lowest dose category, in this category that's called less than 5 millisieverts, one of those units of radiation. To give you a feeling for what a millisievert is, from natural sources of background that we receive every year, we get about 2 or 3 millisieverts per year just from natural sources. That's from the cosmic rays going through our bodies right now, the radon gas that we're breathing, the luncheon that you had probably had a little radioactive potassium and some uranium in it. We're just bombarded by a little bit of radiation, and that's just part of life. And so it's 2 to 3 millisieverts per year. So if you're 50 years of age, then you can imagine just from natural sources you received 100 to 150 millisieverts. And so even in the highest categories of the workers here, their occupational exposure was lower in large than from what would have been received from natural sources. The other thing, just for comparison, what's the annual limit? How much is a worker allowed each year? Millisieverts per year using these units. It's 50 a year. So even here, there's just a few numbers, only 69 in the highest dose category with 200. So when I start showing you these curves, you'll see that there's not much going on. In large part, it's related to the small numbers at the very high dose categories and the overall low distribution of dose of the Rocketdyne workforce. But I also mentioned, though, it was important that we went out and tried to capture total radiation dose. And so we went out to Hanford. We actually went out to 30 different facilities across the United States to capture all the radiation experience that we could from the Rocketdyne workers. And this included the U.S. Air Force, the U.S. Army, the Landauer Dosimetry Company, the Department of Energy, the Nuclear Regulatory Commission. There was quite an activity capturing total occupational radiation exposures. To my knowledge, this is the first time in any radiation study this has ever been done. So this component of the study is also relatively unique. If you look at this, it's supposed to be a light green. This is the dose that individuals had only at Rocketdyne. And then when we added the total dose that they received elsewhere, this is then the dose distribution we used in the analyses that in the higher dose categories it increased the amount of radiation exposure that the workers had. So we took all of this into account into the study. And then again, I mentioned about 1,700 of these workers, of the 5,800, had received dose elsewhere. And a large percentage of them, 25%, had doses elsewhere that was larger than what they had from the Rocketdyne experience. So it was important, we believe, to take all of this radiation exposure into account. So now I've talked about how we identified the population, a little bit about exposure assessment, and made some comparisons with the general population of California. But when we're making more powerful inferences or conclusions with regard to did radiation affect the mortality experience of the Rocketdyne workforce, did exposure to hydrazine or TCE or chemicals or work at Santa Susana, did that affect the mortality experience at working here at Rocketdyne? There we looked at dose response evaluations. And I'm going to show you a series of curves here regarding to actual dose response. For radiation, it will be the amount of radiation that was received. For chemical exposures, since we didn't have a measure of parts per million or any way to make a cumulative measure, we have years worked on a particular test stand or with a particular chemical as our estimate of the amount of exposure a worker had. And so here we'll have these red dots are the relative risks, these ratios of rates, and that indicates the risk an individuals in a group have in comparison to a referent group or comparison group. The reference group is also the no exposure group or the low exposure group. Then we have confidence limits around each one of these points, and that takes into account, shows you the statistical variation, the imprecision of the estimate of the risk. When you see confidence bars that are really large, that means the estimate of risk is very uninformative, chance, statistics, not very powerful. If you find really small confidence bounds, that would be the numbers are pretty good statistics. There's really two types of patterns that I'll be showing you, or that you should have in your minds when I show you these curves. One is, we'll start off with this comparison group, and then there'll be increasing levels of dose. This might be radiation or years worked at Santa Susana. And if you see patterns that increase like this, then that would be indicative that that exposure may very well be associated with increased mortality, because there would be increasing levels of risk. The 1.0 is the norm, the standard, no risk going on. When you have confidence intervals that just hit that dotted line, that means chance can explain it. There's no real statistical evidence for an increase of risk. And so if you have other curves like this that just sort of all bounce around and all the confidence intervals hit that number, the 1.0 line, nothing's going on. Flat, really can't say there's an association. And just for completion, we have this other type of curve where with increasing dose, the risk would decrease, and that also can be of interest, but usually would be attributable to some chance or some unknown confounding in the data. But we'll be stressing mainly these two types of curves when we're doing the evaluations. So the first dose-response curve, this is the risk of cancer among the radiation workers. And so when we look here for the comparison group, or people that had very low or no exposures, and then we have that same distribution of radiation dose to the highest category, did the risk of cancer increase as you increased your exposure to radiation? Reminding you again that these are very low levels of radiation exposure. And this pattern is one of being flat, indicating that there's really no association, no increased risk of cancer associated with these measures of radiation dose. And this took into account not only the Rocketdyne dose, it was the total career dose. One of the difficulties, too, as we look at the higher dose categories, the numbers become very small. Again, there's just slightly over 60 workers who had exposures over the 200 millisieverts, the highest category we had. So it becomes very small and small statistics because of the so few workers with higher exposures. Then we also looked at lung cancer. Lung cancer. Lung cancer was an important site because of the possibility that the workers might have inhaled radionuclides. The work in the so-called powder room, in the development of reactor fuels and materials. They worked with uraniums and plutoniums and varieties of radioactive materials, and there was the possibility of inhaling radioactive nuclides and then this radioactive material lodging in the lung and causing increased dose to the lung. For a handful of workers, the highest radiation exposures that we received, or we determined, actually were for the people monitored, for about 5 or 6 people who were monitored for internal radionuclides and had a meaningfully large dose to their lung. Leukemia is one of the most common cancers, most frequently found cancers seen in populations that have been exposed to appreciable amounts of ionizing radiation. So leukemia was another focus for the study, looking amongst the radiation workers. Again, if you look at the confidence bounds, and some of the risk estimates are very, very imprecise because of the confidence bounds being so large, there is no statistical evidence, if you will, for an increased risk that was statistically significant. But nonetheless, there was a slight excess of about 2 cases compared to the general population, and there was this slight suggestion of a trend. So here we incorporated, even though there was no statistically significant effect, there was suggestive evidence that radiation increased the risk for dying of leukemia. A very valid alternative explanation, however, is that chance is another explanation because of the small numbers and the uncertainty in the data. Might also add, if you look at the numbers, what are the numbers in this high dose point? Well, there was only one leukemia death in persons that received greater than 200 millisieverts, and there was only one in the 50 to 59 range. So again, showing that the numbers are very, very small, and the excess risk, if it is there, is very small based on these numbers. Summary findings from the radiation group. Radiation exposure has not caused a detectable increase in cancer deaths among the Rocketdyne workers. The mean dose was very low. So the exposure distribution among Rocketdyne workers was very low, and therefore this limited the ability to detect an underlying risk if there was one. The radiation doses were just too low. There were no significant trends between radiation exposure and any cancer. Nothing was statistically significant, meaning chance could not be excluded as a possible or plausible explanation for the findings. And the only item that did stand out or we made note of was there was a suggestive trend for leukemia that was based on very small numbers, 18 leukemia deaths observed versus 15.1 expected, but the trend was not statistically significant. Now I've given you the radiation overview, and in the next 7 to 10 minutes, we'll give you the overview for the chemical side. Similar to all Rocketdyne workers, similar to the radiation workers, those men and women who worked at Santa Susana had a lower risk of death than the general population of the state of California. The patterns are very similar. This was also true for a lower risk of dying of cancer, lung cancer, leukemia. So there was no unusual patterns of death when we made comparisons with the general population for all the workers here at Santa Susana. So that's in comparison to the general population. If in fact there was some possibility that because of the rocket engine testing environment or the shipping or the transport of other chemicals or even radioactive materials that were here at Santa Susana, is it possible that those individuals who worked the longest time, were they at highest risk? So what this graph shows is it was tried to evaluate if you worked more than 15 years at Santa Susana, is your risk of dying of a cancer greater, the same as someone who just worked a few years, or someone who worked at Canoga Park? And this graph indicates, with pretty good statistics, because now our numbers are large and we're dealing with all cancers, that there was no evidence that the years you had employed here at Santa Susana increased your risk of dying of cancer. Now focusing down, we had all Santa Susana workers. Now we're focusing in on test stand mechanics, and then the next set we'll look at hydrazine and TCE potential exposures. So now the question being asked is, if you were a test stand mechanic and you had hands-on experience dealing with all these various chemicals and potential exposures to solvents and exhaust gases and oxidizers and fuels, is your risk particularly high or low in comparison with the general population of California? And again, the answer is no. The test stand mechanics had generally lower risk of death than the general population of California. And this was true for all causes of death and for all non-cancers, but for cancers, the pattern of risk was very similar to the general population of California. There was a slight increase of lung cancer, 63 versus 60, but again, not statistically meaningful. I'll just make a quick aside too, when you're looking at these numbers and looking at cancer deaths, cancer is not, when you lump them all together, it's not a rare disease. And the latest numbers from the American Cancer Society, it indicates that for men, 45% of men in their lifetime will develop a cancer. So if you look around, 1 in 2 of us will have a chance of developing cancer in our lifetime. In women, it's lower, it's about 35%, 38%. And so with regard to the probability that cancer will be on our death certificates, it's about 1 in 4. Somewhere between 20 and 25% of all deaths are related to cancer. So when you look at these statistics, and some of the numbers might be large, they may not be unusual when we make comparisons to the general population and from the other underlying causes of cancer in our society. So compared to the general population of California, test stand mechanics did not seem to have an unusual pattern of cancer death. What about the more years you worked as a test stand mechanic? So with these graphs, once again, you're showing you that if you worked for the longest period of time as a test stand mechanic, over 5 years, and some had worked 5, 10, 15 years, there was no evidence, once again, that they had a higher risk of dying of cancer than workers that had just worked for shorter periods of time as a test stand mechanic or to other workers here at Santa Susana. So then we also wanted to focus in on certain cancers, and lung cancer was of concern because of the possibility of inhalation of these various chemicals and causing irritation or damage to the lung that might result in an increased risk of lung cancer. And when we looked for the risk, again, of lung cancer among test stand mechanics, if you see these patterns, they're very, very similar. Really no evidence for any increasing risk by our measure of exposure, which is years worked as a test stand mechanic. So again, even for the specific cancers of lung cancer, there was no evidence for an increasing risk of death. So as test stand mechanics, coming near the end now, talking about hydrazines and then TCE. So the hydrazine groups, there was about 300 that we could identify workers who had worked on test stands, mainly with the small engines, but had hands-on experience with hydrazines. And there was this other group of 200 that we couldn't determine who was who. Probably only about 15 to 20 of them actually did work with hydrazines, so we call them, this group says possible but unlikely. That was just because we couldn't determine who was who. And then we had other test stand mechanics, about 900, who we could not link to any direct experience with the hydrazines. So now when we look at hydrazines and this comparison with the general population of California, there was a lower risk of all-cause mortality, similar to all the other experiences, as being a test stand mechanic who worked with hydrazines. But with regard to the cancers, again, they were either similar to the state of California or slightly elevated. None of these numbers were statistically significant, but for lung cancer, there were 15 deaths that were observed and 10 expected, so there was an increased elevation. So then we wanted to do as our exposure metric. So we have this comparison with the general population of California. What's most important, though, is did those that have the most exposure to hydrazines, were they at the highest risk? So when we looked at all cancers together by years of exposure, potential exposures to hydrazine, again, there is no evidence for increasing risk of cancer in the hydrazine-exposed group. For lung cancer, a similar pattern is seen. No clear evidence for increasing risk with increasing levels of hydrazine exposure. The numbers get to be relatively small, so we have very imprecise estimates of risk as indicated by these very broad confidence intervals. One of the issues, too, that we had discussed with the science committee, that they had suggested that we look at just the no hydrazine group as a comparison group and not just all the other Santa Susana workers. And when one does that, there is a suggested trend, but no clear pattern of increasing risk by years worked. And so we then evaluated the risk of cancer among the TCE-exposed individuals. Again, compared to the general population of California, had a lower risk of dying overall from all causes. But with regard to cancers, they were either similar to what would be expected in the general population or slightly higher. For lung cancers, 51 deaths observed, 41 expected. It was an elevation, was not statistically significant. For kidney cancer, there was also a small elevation, 7 cancers, 3 expected. Again, not statistically significant, but in the direction of an elevation. We then looked at all cancers, and these cancers in particular, to see if there was any increasing risk by the numbers of years a worker was exposed to TCE. And this is the one curve. It's for all cancers. It was also similar for the lung and the kidneys, that when we broke down the workers by how long their exposure was to TCE, there was no evidence for an increasing risk. So it's essentially flat once again. Chemical findings. These would be the summary. Work at Santa Susana as a test stand mechanic or with specific chemicals has not caused a detectable increase in cancer deaths among the Rocketdyne workers. There were no significant trends or any significant excess of cancer among workers at Santa Susana or among test stand mechanics in particular. Hydrazines were not linked to significant increased risks of cancer, although lung cancer was elevated in comparison with the general population. TCE was not linked to any significant increases of any cancers, although lung cancer and kidney cancer were also elevated in comparison to the general population of California. Just 3 more slides. Every epidemiologic study has limitations, and this one is not an exception. Epidemiology is an observational science. It's not experimental, and there's difficulties that can creep in every study. In this particular evaluation, the exposures were particularly low. This was with regard to the radiation exposures, as well as the potential for chemical exposures, which were in large part outdoors with dispersion and dilution from these volatile gases, resulting in a relatively low exposure component for workers. This limited one's ability to detect an underlying risk, given that there was one. The other difficulty is that we didn't know actual chemical exposures. We could only use this term potential. How long did you work on a test stand with the potential for exposures to these chemicals? There weren't any badges. That was different from the radiation, where we feel we had a real good handle on the amount of ionizing radiation the workers received. But the chemicals, there's a weakness there in terms of the exposure assessment. Then there are other factors with regard to lifestyle that we're not able to take into account. This would be diet and cigarette smoking, or any variations of these other factors that can cause disease in our society that we were not able to capture or obtain or address in the analyses. And then finally, this was a study of mortality. It was not a study of illness. It was not a study of cancer incidence. So the conclusions pertain only to the causes of death in the workforce. For many of the major cancers, though, that we were concerned with, mortality and incidence are closely related, such as for lung cancer and also for the adult leukemias. So there were limitations, there were particular strengths, and just to summarize them very quickly, we used a wide variety of sources to identify the workforce. And so we were able to identify 47,000 workers from 1948 through 1999, and we were extremely successful in tracing them. You know, we could use the Social Security Administration, the Healthcare Financing Administration, which is now the Centers for Medicare and Medicaid Services. We were able to use California surveillance program, just a lot of sources to identify whether a worker was alive or if a person had died, what the cause of death was. We had a comprehensive assessment of exposure. We worked with the Oak Ridge National Laboratory, where they spent 3.5 years helping determine the amount of radiation dose a worker had from the ingestion of internal radionuclides. And then we used national resources to determine the radiation dose a worker had once he left Rocketdyne. The chemical exposure assessment, we were able to get a better handle on actual exposures to hydrazines and TCEs because of the findings of these phone books, these personnel listings. So we were able to get a better or more accurate assessment of potential exposures for the test stand mechanics. And then, based on the proddings of our scientific committee, we conducted a relatively enormous amount of analyses. We tried to look at the data in every possible way we could, using different comparison groups, different categories, just a wide range. We made over 5,000 individual estimates of risk, And then for these trend lines, these dose-response curves, we had over 500 trend lines that we evaluated, trying to discern or pick up any patterns of risk that could be tied to the chemical or radiation exposure. We also had, for a referent group, we were able to study the Canoga and DeSoto workforce and the workers there as groups of individuals, those that had not been exposed to radiation or had not worked on a test stand, as in some of the analyses as another possible comparison group. This was our bottom line, our conclusion from all of this research. The follow-up study found no consistent or credible evidence that employment at Santa Susana has adversely affected the worker mortality. Thank you all very much for being attentive.
Thank you, John. He speaks of mortality experience. That's not the kind of thing you want on your resume, is it? Mortality experience. They say when you make a mistake, you have to apologize quickly and grovel. And John went through a great deal of information here about tracking 46,000 people and finding 99.2% of them. That couldn't have been done without Judy McLaughlin. Judy, after 40 years in our HR organization, went to Anaheim, Huntington Beach, Seal Beach, the Rockwell Science Center, every place where an employee has transferred from, and their personnel records have transferred with them, and with a team of other admins went and tracked them all down, and I left her out of the thank yous up front. So Judy, thank you. Apologies here. Now, I'll turn it over to Inger for taking your questions here.
Thank you, and thank you, John. We're going to open it up. I'm sure some of you have some questions. Provide an opportunity to do that. Just to talk about that a little bit, if we could please ask you to hold it to one question each. We'll make our way back around the room. There is going to be a handheld mic out there that you can talk to, or you can come up and talk into this mic right here.
Was the smoker factor considered?
The question dealt whether we were able to look at cigarette smoking. Oh, yeah, so the question was whether we were able to look at cigarette smoking. We only could do so indirectly. From some of the medical records of workers in the 50s and 60s, there was indication for people that were taking certain examinations whether or not they had smoked cigarettes. And so we were able to look at that information in a general sense, and from that one could conclude that some of the workers, particularly who worked on the test stands, appeared to smoke cigarettes more than the general population of the state of California, so that there was a higher prevalence of cigarette smoking based on medical records. We also had done a survey, based on the recommendations for the science committee, of current workers today. And so we sent out current workers or retirees. And it was a sample of some workers, of hourly workers and salary workers. And the question was, did hourly workers smoke more than salary workers? And then the survey did indicate that hourly workers, similar to what's been found in national surveys by NIOSH and other groups, salaried workers, blue-collar workers, smoke more than the salaried individuals. So we were able to obtain that information just in general and be able to help us in making some of the interpretations of the slight elevations of risk when we compared to the general population of California. Was not significant, and we were not able to, well, there was a significant difference between hourly workers and salary workers, that was true, but we were not able to take that into account in the analyses.
Yes, I saw it in the footnote that 1 millisievert is equivalent to 100 millirems of radiation.
Yes.
Okay.
That's right. Some of the units of radiation, they've changed over the years, and the millirem has been a common unit that's been used. In the new international units, they use 1 millisievert, so we had kept with that. But 1 millisievert is 100 millirem. In terms of natural background sources, you get 200 to 300 millirem per year from natural background radiation, to give you a comparable feeling.
I saw there's a question in the back there.
Hi, I was wondering if your study took into effect the radiation worker that worked with trichylethylene.
We were able to adjust for those workers, radiation workers who were test stand mechanics and exposed to TCE. The only way that we were able to get a good handle on potential for TCE exposure was their use as a test stand. So if there was a radiation worker who worked as a test stand mechanic, we took that into account. Excuse me?
Just in one.
No, you could be in both. If you were a test stand mechanic, you could be in the radiation group. If you were in the radiation group, you could be a test stand mechanic. So we thought it was important. In fact, I believe that was one of the recommendations of the science committee, is to not to make them mutually exclusive, to make sure, particularly for the test stand mechanics, where the numbers were so small. You know, we only had 1,600 test stand mechanics, and so if we excluded, I think there was about 182 radiation workers who actually had worked at test stands, that would have been lowering our ability to find any effects had they been there. So we included both together and tried to adjust for their effects in the analysis.
Thank you.
Dr. Boice, the first chart you showed on the measure of radiation dose said excluding leukemia, and I didn't quite understand why it was important to exclude that, and would the data have looked differently if it wasn't excluded?
Right, very good question. And in studies of radiation, this is what's normally done, standard procedure. You look for all cancers, excluding leukemia, and then 2 slides later, you just look at leukemia. So you look at them separately. So I would just start following standard procedures. We did do the analysis where we included leukemia, and there was no difference in the patterns of risk. Again, there was only 18 leukemia deaths. So that made no difference, and was just following the normal procedures so that we could discern whether there might have been an overall cancer effect, whether there was an overall leukemia effect.
How does the general health of the population in California relate to or compare to the general health of the population nationally?
It's better. In fact, the question was, how does California compare to the United States? And it was real interesting. We made that comparison. We compared the observed number of deaths to the state of California and the entire population of the United States. And when you did that, you're really healthy. Okay, I just want to make that compare. It was just shockingly a big difference. California, whatever y'all are doing, it's pretty good because you're better than most of the rest of the United States with regard to mortality. We also then experiences. We also looked at the county mortality. We looked at Ventura and Los Angeles County to say, well, gee, how does California compare to the local counties? It was almost exactly the same. So because of statistics and better numbers, we use California for the comparison group.
One of the great weaknesses from the UCLA study was the size of the study group, leading to not much statistical significance. Could you kind of talk about how that relates to this study?
Yes. We did an intense effort, and as mentioned, working with the Boeing staff and Judy McLaughlin in particular, to track down all sources of worker populations. And so our population size is about 30% larger than the UCLA study. So in terms of getting more numbers of workers, we were able to capture more of the older workers, and we used those phone books, and we went back to other areas where workers had taken their work histories to try to capture as many as we could. So our study size is larger than the UCLA one. Nonetheless, after saying that, it's still, the numbers are not very big. So even though our radiation work group that we studied is 1,000 or so larger than what the UCLA investigation was able to evaluate, 5,800, 6,000 is not large for a radiation study. And so they're much larger studies. So the ability to find it's the same, almost the same concerns are raised. The ability to find effects in those small numbers who received high doses, it's very limited.
I have a question here. The number of people that I personally know that may have died of cancer is a very small number of these people that were exposed to these agents. And that number would be so small that you couldn't compare it to a statistical large number. And how many people were actually found that were exposed to any of these agents that could actually say they died of exposure to any of these agents? Was there any of them at all, one or two? They're saying here that nobody was exposed to this stuff had any reaction.
Epidemiology cannot determine whether a cause of death was actually linked to a particular exposure. We can't do that. All we can do is, was this population of workers who were exposed to hydrazines, did they have more cancer than workers who were not exposed to hydrazines? And so we looked for those associations, and as presented, there was just very little evidence that the group of workers exposed to hydrazine had higher risk of death or higher numbers of death for any particular cancer than comparable workers or low-exposed workers.
Is hydrazine or any of these other agents known to cause cancer?
In animals, animal studies have indicated that hydrazine can cause cancer. Radiation clearly is a carcinogen, and there's numbers of studies, worker populations, that show that radiation at sufficiently high levels can cause cancer. Same thing with TCE. The epidemiologic evidence is building. There is some evidence that high exposures to TCE could be related to a number of cancers in humans. Clearly has been shown in animal experiments. One of the things, the key thing here is dose. We're all being exposed to radiation right now. It's very unlikely that much, if any, of the cancers that will develop are related to this low levels we're receiving now. So if you have low dose exposures, it's just very unlikely to be able to attribute cancer death to an individual or even to a group of individuals to that exposure. The same with the chemicals. The chemicals were different than in the type of exposure because it was outdoors. There was this opportunity for the volatiles and the dilution and the dispersion, as opposed to some workers in other aerospace industries where they're working with vapor degreasers and they have TCE and these other potent chemicals in enclosed spaces in the early days without respirators, continually, lack of ventilation, where there's more potential for high exposures and the probability of finding adverse effects if they did so exist. So I try to make a distinction there between epidemiology can't determine an individual causation factor, can't do it, we just can do associations. And then the situation here is the exposures are pretty low.
That's what I was getting at. The people that I know of that died of cancer probably had excessive exposure, but there were too few. There's maybe only a half a dozen that I could think of. But there's too few to make a study out of.
And if in fact, I think I hear what you're saying, and if you look at our high dose exposure group, say in radiation, there was only 63 people. 60 total who had, or 69 people who had more than 200 millisieverts. That's just a small number. And so if there was an excess of one case, the epidemiologic study would not be powerful to detect that. Thank you. Certainly right.
If I remember correctly, and I could be wrong, the UCLA study found significance when they took discrete types of cancers and started grouping them. I don't know if it was like kidney and lung, and in your study you talk all cancers, and then you broke into discrete types. Did you consider grouping, or is that something that, or what was your take on that?
Yes, we reproduced all the types of analyses that UCLA had done, and we had conducted analyses, in these these thousands of evaluations we did group some of their cancers together and looked for any patterns of risk that might replicate them. We were not able to find any significant, that's the bottom line, when we did the groupings. Some of the groupings we did not feel were strictly appropriate epidemiologically because of lumping together leukemias with lymphomas. That was one of the rubrics or categories that they did. And we have found that it was best to separate them out and look at them separately. They have different causes. Radiation causes leukemia. Radiation is not known to cause lymphoma or conceptus. So we did them separately in our analyses. But for completion, we did put them together. They also used another series of sites, aerodigestive, by lumping together some different categories here in the upper respiratory and digestive tract, and we did look at those analyses and didn't find anything unusual in those patterns. So, yeah.
Are there any additional questions? I'd like to thank you all for coming today. I'd really like to encourage you to please take some time to come and talk one-on-one with our science committee members or with our research member here, and look at the poster boards and make sure you get a copy of all the materials that are listed up here. And we thank you for your participation today. Thank you.